Hello. Have you ever had those Siete chips? They're like the grain-free, dairy-free, gluten-free, vegan, whatever. Not really chips. Oh, Siete, they're in the orange bag. They have a no salt kind. Okay. The reason why I bring them up is because I had a bag yesterday before I went to bed because I was just like stressed eating. And I woke up an hour later today. I'm just like, ah. So now I'm here at 5:20 instead of 4:20. So we're like, I mean, it doesn't really matter either way because we're only doing these lightning problems now. This is, okay. Hold up. But I'm just saying, like, okay, so, like, hey, be a field. Whatever. My pen is messing up. Okay, hold on. Compute the dimension of k over k, over k. Hold on. Now this is throwing me off. Over k of. Look at it. This is that. Kx is a ring. Kx is a field. I mean, K is a field, so when you add an indeterminate, it's not just a ring, it's like a really nice ring. It's a Euclidean domain, even. It's a PID, even. So, I mean, what does that give us? A headache? So we have the mth power is going to, anything higher than m is going to have to, like we have this, so recall, if we have x to the m to the p equals x to the mp, or if we have, no, that's like the main one. What's another one we need? No, I think that's like it. Like, the reason I say that is because once we get to higher powers, like let's say we have x to the m plus 1 equals x times x to the m, right? And this isn't the ideal generated by m, just parentheses. So once you get to higher powers of m, they get reduced mod dimension equals m or something. That's maybe not the nice way to say it, but what I'm saying is that anything higher than m won't survive. Anything higher than m will be in the ideal generated by m. So we're only looking at, so elements of k adjoin x mod the ideal generated by x to the m will be of the form, let's say we have, let's do this. This is a polynomial, okay? So we have a naught. Maybe I'll just put p, because this is like the standard, right? a1x plus a2x2. We know this, right? Plus a m minus 1 x to the m minus 1. That's what we're looking at here. And then same for, let's say, q, elements of, and they're over the same field, so it's like kind of nice, or like it's pretty, you know. It's not giving us like, I don't want to put equals, and for q, we'll just put like that, or not implies. Okay, b naught plus b1x plus b2x squared plus plus bn minus 1 x to the n minus 1. So what's going to happen with these polynomials? Like, so a tensor product is going to take all multiplicative combinations of these And we already see what happens when we have like this. Like let's say we have how do I write this? See, I just want to write another example. I'll put a comma maybe because they're not. I'm not saying they're on the same statement, but let's say we have x to the m to the n, right? Then we have x to the m n. But this, so that's like the worst. Let's call it the worst possible case, right? The worst possible. I mean, is that like how you say it? I guess yeah, that's what I'll say. The worst possible case. So if we have m and n as a product, what's the biggest product m and n can have? So if m and n are coprime, then m and n then m I mean that's it. That's the that. When I say worst possible case, I think I'm either speaking of maximality or minimality, depending on like what you're studying. But if they're coprime, then this product is just this product. You'll get all of the m terms, you'll get all of the n terms. This is what I'm saying. And then you'll have m and n copies of something. If they're not coprime, then you get common divisors, which reduce the power of which reduce I mean, we'll just leave it at that. So compute the dimension of k. So now we have, okay, hold on. So now we have goal. Compute dimension of k. Do they mean, okay, hold on, over k? I keep saying of k, but I mean over k. Compute dimension over k of k is x. So what's the dimension then? The dimension would have to be what? Like seriously. Let's ask lambda. Hold on, how to find it. Wait, where is it? Did I not have the fall 2000? Oh, here we go. Hold on. Hey, lambda. Hold on. La 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 la. We're waiting. And as we're waiting, you can use the hints that I gave you to come up with a solution. So, as k vectors, this is what I was saying, right? Elements will be of the form. This is as k vector spaces. I actually should have said that. As k vector spaces. As k vector spaces. And now we're just doing, yes, as k vector spaces. So then equals x n minus 1 and then x span no, never. I'll never write my thesis ever. X to the n minus 1. Okay. Dimension of k equals n. And we already got that, right? We already knew that there were m of these and then n of these. I'm saying m of these and then n of these. We already knew that. That's what I was saying. Every element looks like this, and this is exactly what vector space elements look like. I mean, you can even, if the coefficients are in a field, like immediately you're just gonna be like, yeah, this is vector space structure. I should have probably said that. I said PID. I was talking about the ring. I was thinking about it as a ring because I'm like conflating it with it as an algebra instead of looking at it as a vector space. So sometimes I get those mixed up. So now we have, okay, so step 2, computing tensor product of finite dimensional vector spaces. So recall again, these are just basic tensor product facts that we actually should be giving to elementary school kids. So if you're watching this, your elementary school, congratulations, you found the right place, because this is that simple. Once you study the pattern, it's not too bad, right? Look, so that's it. And then applying to our case, but it's saying, look, it says K. This is what's throwing me off. The notation is using this. It didn't put it over K X. It put it over K. Like the problem says compute the dimension over K. So that's a vector space computation, but this notation is saying K adjoin X for the tensor, which is like something else. That's why I was getting confused, and I don't know if it's a typo or if it's actually like significant. Equals m times n. That I mean, that's what we said. That's it, because that's the only thing you can get. Is m times n. So yeah. But so yeah, I guess that's it. Like that's the problem. It's a little bit like it was faster than I thought. I thought it was gonna take more work, but I mean, I gave you the polynomial explanation why, and then you see the elements as polynomials, or you can see them as vectors. That's kind of like the whole thing with the whole like finite dimensional coefficients in a field thing, is that polynomials are represented by vectors. So as soon as you get like this polynomial ring over a field, you can look at it like a vector space, and we know how to take tensor products of modules, and we know what the dimensions of the vector spaces are, and we know that tensor products are geometrically encapsulating multiplication, and so we just take the multiplication of the highest powers, and then that's it.